Welcome back to the Open Polkadot Bootcamp. I'm Jinjun, and today we're gonna learn about XCMs. Throughout the Open Polkadot Bootcamp, two last videos about XCM, you already learned about fundamental knowledge about XCM, what is the location, multi-asset, and also the overall architecture. Today we're gonna dive deep into how you can transfer in XCM the journey of the XCM instructions, and also the architecture of the XCM executor. We're gonna move to the demo section, how can you configure the XCM executor yourself. Even though XCM is designed to be general and agnostic based on what we already learned about the four attributes of XCMs. However, there are also a few initial use cases of XCM. The first one would be remote transfer. Imagine we might want to simply control an account on a remote chain. The remote chain here is a chain B, allowing the local chain, which is a chain A, to have an access on the remote chain for receiving funds and to eventually transfer those funds it controls into another account on that remote chain. So chain A have an account on chain B that allow the chain A to transfer the fund from chain B, Alice, to Bob on chain B. Then there are another use case called teleport. Teleport is very common in the blockchain world, where you mint token on one chain and burn token on the other chain. And it's simply have the token teleport from chain A to chain B, because that disappear on chain A and then reappear on chain B. So imagine a token such as USDT or USDC, which has instances or perfectly fungible on several different chains, and it should be possible to burn such a token on one chain and mint a corresponding token on the another supported chain. So in the balance of XCM, we call this teleporting, owning to the idea that the apparent movement and asset in fact happen by destroying it on one side and creating a clone on the other side. Then finally, there may be the two chains would want to nominate a third chain, one on which an asset might be considered native to be used as a reserve for the asset. And as usual, after we learn about the theory, we're gonna move to the code. In this section, we're gonna learn how the XCM's virtual machine gonna combine the instructions and then execute it to support the initial use cases that we just mentioned. The first one will be the transfer. And as we already know, the transfer is very simple from one asset to the another asset in the same local chain. So right here, the context would be you have one blockchain, and then you want to transfer from inside that one blockchain from the account A to the account B. And how this look like? The first instruction that we would use is the withdraw asset. The withdraw asset instructions is the most common way to get asset to the holding register of the XCVM. The multi-asset in the operand will be stored in the holding register to be later used for other instructions. So as we seen, so we can use the expressions here, amount, to take a certain amount to the native token. This here amount is the location in the asset that we already learned. So here is the parent, and the asset, and the amount is the value of the asset. And what does mean is it's point to the asset of the current change with the total amount. The second one would be the buy executions. So the buy execution instructions is responsible for requesting more execution power by paying the fee. So because XCM is designed to be agnostic to the underlying consensus system, like Ethereum or Polkadot has two different fee model. So this instruction let you pay for the execution of the XCM using the asset in the holding register. So most XCM are not allowed to be executed, blocked by the barrier. So if they don't contain the instruction as one of the first one to pay for the all feature one. That means in the XCM executor, there's the configuration called a barrier. We're gonna learn about this later in the XCM executor architecture. But without containing these buy executions, then most of the instruction won't be executed because you have to pay for the fee. Then after you withdraw from one account to the holding register, you want to bring the amount token from that holding register out and then pay and then give it to the destination. Then you have the another instruction to deposit called a deposit asset. This deposit asset accept the asset. This one is the multi-asset filter, like what you learned in the multi-asset video. The multi-asset filter accept not only the wildcard asset but also multiple asset. And in that way, you can deposit the asset from the multi-asset filter to the beneficiary, which is the multi-locations. So this instruction, we put the asset from the holding register that match the multi-asset filter into the beneficiary. Note that the beneficiary must be a location where the local consensus system can actually deposit asset to. And over here, we have the example for this combination of instructions. So when you want transfer, the first one will be like withdraw asset. We withdraw the asset from the current local consensus system with the total amount of the asset that we want to transfer. Then we buy the executions that we pay for the fee using like the one in the holding register, the fee here amount, and also the weight limit. And then like you have another instruction called deposit asset that you want to deposit the asset to the multi asset, like you want to deposit the asset or and beneficiary the account ID 32 to the account like Alice. Now we move to the asset teleportations. So as you can see in the diagram over here, like we have like 2 different instructions involved in this process. The first one will be like initiate teleport, receive teleported asset, and the deposit asset. And I think that it is very straightforward. Initiate teleport, that means like you kickstart the teleport process, that you withdraw the token from one account, burn it, and then call another instruction like receive teleported asset to send that token from the source to the destination. Tell the destination that like this token already burned, and then like you ask the destination to deposit the new asset to their account. But like actually the process under the hood is more complicated than that. So we're gonna learn right now about initiate teleport. The source like gather the asset to be teleported from the sending account and take them out of the circulating supply. Taking note of the total amount of the asset that were taken out. Receive teleported asset. The source then create an SCM instructions called like receive teleported asset and put the amount of asset taken out of circulation, and then let the receiving account as parameter to these instructions. It then sends the instructions over the destination where it gets processed and new assets are put back into the circulating supply accordingly. The destination then deposits the asset to the receiving account of the asset. So as you can see right here, it's used the two phrase like taken out of circulating supply and put back into the circulating supply. So this gives an indication of how much flexibility an SCM executor has in implementing the semantic of taking an asset out of and putting it back into its circulating supply. So it's imagine like the circulations of token of like the overall cross-chain network is the same, like it's used in your share across like the network. So like if you taken out the token from one chain and then send it to the another chain, then you have to put back to the circulation. If it's not like put back correctly, then like there's gonna be like a lot of problem happen. For example, if you send an NFT from one chain to the another chain and you take it out of circulations, but like you don't like put it back into the circulation, then now like the token circulation is already like be incorrect, because like now you might have like the duplicate token on one chain, or you have like missing a token when you sending it to the other chain. The reason why it say like taken out of circulating supply and put back into the circulating supply, because there are actually like a lot of method that you can apply here to do that, to do like the transferring. But like right here, like it's used like burning. So like when you burn the asset, that means that you take them out of circulations. This means it's already disappear. And then when you want to like make the circulation correct, then you have to mint a new token on the other chain. So put back the asset, that's mean like minting the another chain. When you send already sending it and the other consensus system receive that. So what is the disadvantage of this model? So the disadvantages of this model that is require both the source and the destination to have a high level of mutual trust. That means like the source and the destination have to trust each other. So in that case, like when you mint or when you burn, those things have to happen in the correct way, because as I already mentioned, so if like you cannot just the teleported destinations. So when you already like burn your token, they don't mint the new token. That means that you already lost your token, and that is not like the way that you want it to be. That is not like the way that you want it to happen. Now we're gonna take a look at the example. So here's like the following example that achieve the process that we described above. Before we initiate the teleport, we have to withdraw the asset from the pool first. So as we already learned in the transfer, so withdraw assets, that means like withdraw the asset from the account of the current Gen A and put it to the holding register of the XCVM. Then the another instruction is processed called initiate teleport. This bring the asset to the destinations to the destination parachain 1. with the SCM. Here's the SCM is the vector of instructions that we're gonna process on the destination chain when they already receive the asset. So we process the deposit asset that we want to deposit this token to the account ID 32 Alice when it's already arrived to the parachain 1. But initiate teleport. So this instruction is intended to be executed from the source system. So it takes the asset to be teleported that match the multi-asset filter from the holding register, which needs to have been populated. And usually with a virtual asset instruction, it then sends an ECM to the destination system given by the destination with the following instructions. So it's receive, clear, and all instruction from the ECM operand going to be executed. And the thing that you have to, the thing that should be noted down here is that the receive teleported asset and the clear origin is always added when you call an initiate teleport. So when you initiate a new teleport, this method, these instructions receive teleported asset going to be added automatically, and also the clear origin. Why we needed the clear origin to be added in this case? So because we don't want when everything is done, the destination change can still use the origin, the style origin that you send to that change to manipulate some kind of instructions, and then using the asset of that origin. So we don't want that. We don't want any malicious actions are going to happen. So you have to clear the origin. Receive teleported asset. So this instruction is adjusted indications. Remember, the source have to adjust the destination if you want to do the teleport. And it should only be executed if the origin of the ECM is adjusted for the purpose. This level of care must be taken because of this instruction. We put the asset into the circulating supply, usually limiting them. So as specified earlier, this can result in an increase, decrease in circulating supply of an asset, or duplication loss of an NFT if the source is not adjusted for this purpose. So you can set which origin are allowed to act as teleporter by configuring the is-teleporter. This one is also the configuration of ECM executor. Type in the ECM executor. So if the origin is not allowed to teleport the asset, there's going to be an error throw. And this instruction will populate the holding register with the teleported asset, withdraw, and then call receive, it populate the holding register. Okay, so now by the clear origin is also described here. So this instruction clear the origin register of the ECVM, and it's used to not allow the further instruction to act on behalf of the previous origin. We don't want that to happen again. Another example. So we have withdraw asset, initiate teleport. Very simple. Whenever you want to teleport the token from chain A to chain B, to adjust it chain B, then you just simply call it withdraw asset and initiate teleport. And that's how the asset teleportation happen when you use the ECM language. Taking a look at the code of the teleport asset. So in the process instruction method of the ECM executor that we already visit in, I think in the last two videos, the initiated teleport, that here's the code of the teleport. So you can see it right here. This take the asset from the holding register, and then we iterate to all the asset and then check out. We're gonna learn about the asset transactor later when you visit the ECM executor sections. We already take the asset out of the circulations because the withdraw asset is called before this initiate teleport. There's a re-anchor method here. I don't know what this re-anchor method gonna do, but we're gonna learn that later. Then you have the message that you have the receive teleported asset, and also the clear origin. We want to send the ECM sender gonna send this message to a destination change with also the list of all the ECM message that we define here. And that's how the ECM initiate teleport work. Then how about on the destination change? So when you send that message and it is processed and executed, then there's gonna be a few other instructions sent to the destination change. The wood one would be added automatically, not from yourself, but from the ECM executor, the receive teleported asset. That's how the destination change to receive this teleported asset from the source change. Then the clear origin, as we already learned, by executions, and also deposit asset Then later on, like we have like the receive teleported asset, and you can see like the receive teleported asset is used like the local consensus system origin, and check whether we just the origin to teleport the asset to the current change. If it's a teleporter, then we accept or we throw this error. And if it can accept, we check in. We check out the asset. We check out the asset. That means we bring the asset out. And then we check in the asset. Then we go to like all the asset and we subsume the holding register. And that is for the asset teleportation. How about the reserve back transfer? Different from the teleportations, you have like the source chain and the destination chain have to just its order. So let's say like if like you want to transfer the asset from chain A to chain B, but like the chain B cannot just chain A, and likewise. So what happened here? So one way that like for both chains to transfer the asset across the two chains is to rely on another third party change, and here like we call it a reserve change, and this allows like two consensus system can transfer the assets across like the blockchain across the network and relying on the reserve asset on the another change. What there is to do is like on this reserve asset, both source change and the destination change have to register an account on the reserve blockchain. Then like the source change is gonna have the derivative token, mean a new derivative token, have like a derivative token reserved back by the asset, by the real asset actually like exists on the reserve change, and the destination gonna have also like have a derivative token backed by the asset on the reserve chain as well. So in that way, like let's say like if the source change and the destination have any problem like in between, it doesn't like happen on the real asset, but it's actually just a derivative token. And in that way, like the circulation doesn't be taken out or taken. The circulation still remain the same across like the transfer, because like the token is actually not teleported, but it's just be the derivative token is teleported. And what it do is like you need a few instructions here. The first one will be like initiate, reserve, withdraw, similar to the initiate, teleport. Then you have like withdraw the asset from the reserve, then like deposit the reserve asset to the account of the destination blockchain. Then you let the destination blockchain know about the reserve asset deposited, and the deposit asset happen on the destination. So the flow would be here, let the source gather the derivative asset to be transferred from the sending account. The source gonna have like an account called a sending account, process the derivative asset, and it transfer initiate the reserve withdraw the derivative token from the source, and it's transferred to the reserve change. And in the reserve change, there's instruction like withdraw asset that it withdraw from like the sovereign account here, withdraw the real asset from the reserve change, and it's deposit to the account of the destination on this reserve change a real token. Then it let like the destination know by these instructions about this event, and it's the derivative token going to be added to the destinations. And as you can see, like the source chain and the destination chain doesn't have to just each order, but there are also like a few drawbacks in this model. So the additions of a third consensus system is already a hint of the disadvantages of a reserve asset transfer model. So firstly, the reserve could easily become a point of centralization when too many consensus systems rely on it, and to be the reserve of choice for the asset. So let's say like, imagine like you have like 1,000 parachains in the Polkadot network, and like everyone like rely on the asset hub or the relay change for the reserve asset. The asset hub gonna like become a centralization of asset for like all these new reserve transfer happen there. And secondly, like the sheer amount of steps required necessarily make it more prone to error. And there's a lot of as you can see like in the diagram, there's more instructions happen compared to teleport. So you have to initiate, withdraw, then like deposit, and then like reserve and asset deposited, and then deposit asset. And there's like 5 instructions in total. However, like in asset teleportation, you only have 3 instructions in total. So the implementer, like we have to consider more possible pitfall and provide a technical support accordingly when an end user encounter issue arising from this step. And last but not least, like either the source or destination can opt to designate the multiple consensus system to be their reserve. So in such a situation, care must be taken out in order to ensure that the sovereign account or the reserve are balanced, so that the one doesn't get drained while the other still contain a healthy balance. So when you want to, let's say you want to send the asset across a multiple consensus system, and each consensus system they have they want to designate they just to a specific reserve as blockchain. And that way you have to open the reserve account, or we call it the sovereign account on that specific reserve change. And then that way you have like multiple account on multiple reserve change, and then your responsibility now will be more. There's going to be like an overhead in the responsibility of the one who's going to manage all these account for like reserve back transfer. And a note on the just. So we mentioned that reserve back transfer require the sender and the destination to just a third party, the reserve, and not each other. So this is true, but it doesn't mean the sender and destination have to trust it's only the reserve. They also have to trust the issuer of the token. Whenever you are dealing with a particular asset, you always trusting the issuer of the asset, because at any point they could mint a huge amount of that asset and wreaking the havoc. So you have to make sure that you trust the asset based on the security mechanism used to protect its issuance. For this reason, like reserve work best when they are the issuer of the asset being transacted. In that scenario, you only have to trust the reserve, period. And here like we have the example of the reserve. You have like the first message, withdraw asset. So you withdraw from the parent blockchain the amount, and then you initiate the reserve withdrawal. You reserve of the reserve now going to be the parent. The parent who could be like the relay change. Then you call it like XCMs. Then like this ECM gonna like contain like the deposit reserve asset. You send to the destination blockchain like parachain 2. Imagine like you are parachain 1, and then you also like have the ECM deposit asset that you add to the account list on that deposit reserve asset. And this new ECM like contain the following instructions like withdraw asset, clear origin, and all the instructions specified in the ECM for the initiate reserve withdrawal. For the deposit reserve asset, then you have like reserve as asset deposited, clear origin. Reserve asset deposited is gonna be when the parachain 2 receive the ECM, it's mint a new derivative token and deposit them locally to the beneficiary account. The reserve asset deposited is adjusted indications. So as is the case with teleporting, you need to adjust the reserve to have actually put a specified amount of asset in the sovereign account of the system. So you can specify which system you adjust as reserve for which asset by configuring the e-reserve type in the executor. So even though it's also reduce the just between the source chain and the destination change. However, you also like need to specify the just indications for the reserve change, because right now you will receive like the reserve asset deposited from that reserve change, and that's going to be the process to the e-reserve. This one also the configurations of the SCM executor. And both parachain have to just the third party reserve blockchain or just the relay chain and reserve for its own native token. Now, aside from the transfer, I also want to talk about the Transact. And Transact is also a very interesting instructions in ECMs that allow you to like execute any like runtime call. That allow you to execute like any like frame-based system runtime call, or also like EVM smart contract function call across like the change. So right here like you have like the Transact instructions with the origin, require wait, and then call. Like this call is like the most important one. It's like encoded, the encoded call. So it's you like double encoded. It's gonna have like the encoded, which is a vector U8, and the decoded is the option type of the decoded type, T, generic type. One thing must be noted out that the ECM is a consensus system agnostic, as we learned in the 4A. So it does not to know what is being encoded in the code field. So hence like the field is a bivector that like can be freely interpreted in whatever form possible. You can send like basically a hello world string and encode it into a vector U8 and pass this into a double encoded call, and no one knows like what this means because it's simply a bivector. So however, like the XCVM does not inherently know how to interpret this call field or nor like how to decode it. So it's reliant on the t-type parameter to specify the proper codec for the bivector. So instead of just using a vector U8, we use a double encoded as a wrapper around a pre-encoded call vector U8 with extra functionalities as like catching of the decoded value. So we like to emphasize that the call in the Transact instructions can be anything from a runtime call in frame-based system to a smart contract function call in an EVM-based system. Each CVM has a Transact status register to record the execution result of the call that's dispatched by Transact instructions. And the flow of the ECM's executor gonna process to this Transact is like decode the call field into the actual call that we want to dispatch. Check with the self call filter to see like if that call can be dispatched on the change to whether the execution of this call is allowed. Use the origin converter to convert the multi-location to the runtime origin. So when you already involve the runtime call, it's gonna be different type of origins. So you have to convert the multi-locations. So check whether the call weight doesn't exist, the required weight as most. We have to set the limit for the weight. Dispatch the call with the converted origin and set the Transact status register to be the result of the dispatch. Calculate the weights that were actually used during the dispatch. So this first example for that Transact is like you have the call like balances. So this balances like you want to set the balance of Alice, want to set the balance of the native token of Alice to like 5 multiply with amount, and then like you can call a withdraw asset by the execution and then transact that call to populate that amount to the Alice account using the Transact. The example 2 would be NFT. So in this example, like as per Gen 1, we create an NFT collection on the relay chain and then we mint an NFT with ID 1. The admin of the NFT collection is per Gen 1. Then like you have the method like create a collection with ID 1. The admin is the per-chain sovereign account ID 1 on the per-chain 1. Then like you gonna like call you mint a new token on the relay chain for that per-chain account, sovereign account. And that's how this is how like you can send a message to a relay chain to create a new like NFT collections across like the blockchain. And that's also the end of today's section, and I hope that it's already like give you an overview of like the journey of the ECM, like how you can like make transfer using ECM. Like we learned about like asset teleportation and reserve back transfer, and also like how to transact that like execute any runtime call or any like smart contract function call using the ECMs.